The Fermi Paradox, where is everybody? The Fermi Paradox is one of the most profound and unsettling questions in science. If the universe is so vast and ancient, why haven't we encountered any signs of extraterrestrial intelligence? The paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual conversation about the likelihood of extraterrestrial civilizations. At its core, the Fermi Paradox is a contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. Let's break this down in extreme detail, exploring the contradiction and its possible resolutions. The contradiction, a universe teeming with silence. 1. The universe is incredibly old. The universe is approximately 13.8 billion years old, and the Milky Way galaxy, which is just one of an estimated 2 trillion galaxies in the observable universe, is about 13.6 billion years old. This immense timescale means that there has been more than enough time for civilizations to rise, develop advanced technologies, and potentially colonize the galaxy. Star formation in planetary systems. The first stars formed within a few hundred million years after the Big Bang, and the first rocky planets likely appeared within a billion years. This means that planets capable of hosting life have existed for billions of years. Time for evolution. On Earth, life emerged relatively quickly, within a few hundred million years of the planet's formation. Intelligent life, humans, took about 4.5 billion years to evolve. Given the age of the universe, there has been ample time for other civilizations to rise, even if their evolutionary paths were slower or more complex than ours. 2. The sheer number of planets. The Milky Way alone contains an estimated 200 billion stars, and recent data from the Kepler Space Telescope suggests that most stars host planets. Conservative estimates indicate that there are tens of billions of Earth-like planets in our galaxy, planets within the habitable zone where liquid water could exist. The Drake equation, this famous equation, formulated by astrophysicist Frank Drake, attempts to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. While the equation is highly speculative, even pessimistic estimates suggest that there should be at least a few civilizations capable of interstellar communication. The Copernican principle. This principle states that Earth and humanity are not special or unique in the universe. If life and intelligence arose here, it should have arisen elsewhere as well, given the vast number of similar environments. 3. The absence of evidence. Despite the high probability of extraterrestrial civilizations, we have found zero evidence of their existence. This absence of evidence is not just a lack of radio signals or spacecraft, it extends to the absence of megastructures, like Dyson spheres, interstellar probes, or any other signs of advanced technology. The search for extraterrestrial intelligence, SETI. For decades, scientists have been scanning the skies for radio signals or other technosignatures that could indicate the presence of intelligent life. So far, the results have been completely silent. The Fermi Paradox in action. If even a single civilization had achieved interstellar travel and colonization, they could have spread across the galaxy in a few million years, a blink of an eye on cosmic timescales. Yet, we see no evidence of such colonization. 4. The implications of silence. If intelligent life is abundant, the galaxy should be teeming with activity. The fact that we see nothing suggests one of two possibilities. Intelligent life is exceedingly rare, and we might be alone. Something is preventing civilizations from reaching the stars or making their presence known. This contradiction is the heart of the Fermi Paradox. The universe seems primed for life, yet it appears empty. Possible resolutions to the Fermi Paradox. The Fermi Paradox has no definitive answer, but scientists and thinkers have proposed numerous hypotheses to explain the apparent silence of the cosmos. Let's explore these in extreme detail. 1. The Great Filter. The Great Filter is the idea that there is some nearly insurmountable barrier preventing civilizations from reaching the stage of interstellar colonization. This barrier could exist at any point in the evolutionary timeline, from the emergence of life to the development of advanced technology. Life itself is rare. The transition from non-living chemicals to self-replicating life might be extraordinarily unlikely. Even if the universe is filled with habitable planets, the actual emergence of life might be a cosmic fluke. Intelligence is rare. Even if life is common, the evolution of complex, intelligent life might be exceedingly rare. For example, Earth has had life for 3.5 billion years, but intelligent life, humans, has only existed for a tiny fraction of that time. Self-destruction. Advanced civilizations might inevitably destroy themselves through nuclear war, environmental collapse, or misuse of technology. This is a particularly grim possibility, as it suggests that technological progress might be a dead end. Interstellar travel is impossible. The laws of physics might make interstellar travel so difficult that no civilization, no matter how advanced, can achieve it. For example, the energy requirements for traveling between stars might be prohibitively high, or the timescales involved might be too long for any civilization to sustain. The Great Filter is a sobering concept because it implies that the future of humanity might be bleak. If the filter is behind us, we are incredibly lucky. If it lies ahead, we might be doomed. 2. The Zoo Hypothesis. The Zoo Hypothesis suggests that extraterrestrial civilizations are aware of us but choose not to make contact. This could be for a variety of reasons. Non-interference. Advanced civilizations might have a policy of non-interference, allowing younger species like humanity to develop naturally. This is similar to the Prime Directive in Star Trek. Scientific observation. We might be part of a cosmic experiment or observation project, with aliens studying us like animals in a zoo. Ethical concerns. Contacting us might be seen as unethical, either because it could harm us or because we are not yet ready to join the galactic community. The Zoo Hypothesis raises questions about the ethics of contact and the potential consequences of revealing ourselves to a more advanced civilization. 3. The Dark Forest Hypothesis. Inspired by science fiction, the Dark Forest Hypothesis posits that the universe is a dangerous place, and civilizations remain hidden to avoid attracting the attention of hostile entities. This idea is based on the following assumptions. Resources are limited. Civilizations might compete for finite resources, leading to conflict. Survival is paramount. Any civilization that reveals its location risks being destroyed by a more advanced or aggressive civilization. Mutual distrust. In the absence of communication, civilizations might assume that others are hostile, leading to a shoot first, ask questions later mentality. The Dark Forest Hypothesis suggests that the cosmos is a place of constant threat, where survival depends on secrecy and caution. 4. We're first or last. Another possibility is that we are among the first intelligent civilizations to arise in the universe, or among the last. We're first. If the conditions for intelligent life have only recently become possible, we might be one of the first civilizations to emerge. This would make us pioneers in a young universe. We're last. Alternatively, we might be among the last remnants of a dying cosmic era. If most civilizations have already risen and fallen, we might be living in the twilight of galactic history. Both scenarios are humbling, as they suggest that humanity occupies a unique place in the timeline of the universe. 5. Other possibilities. We're not listening correctly. Our search for extraterrestrial intelligence might be too narrow. For example, aliens might use communication methods we haven't discovered yet, such as quantum entanglement or neutrinos. They're too alien. Extraterrestrial civilizations might be so different from us that we can't recognize their signals or technology. They're hiding. Advanced civilizations might deliberately conceal their presence to avoid detection, either out of caution or for other reasons. So, where is everybody? The Fermi Paradox forces us to confront the possibility that we might be alone in the universe, or that the universe is far stranger and more dangerous than we imagine. The absence of evidence for extraterrestrial intelligence is not just a scientific mystery, it's a profound existential question. Are we unique? Are we doomed? Or are we simply not looking in the right way? The Bootstrap Brain Paradox. Are you real? The Bootstrap Brain Paradox is one of the most mind-bending and unsettling thought experiments in modern physics and philosophy. It challenges our most fundamental assumptions about reality, consciousness, and existence. At its core, the paradox asks, how do you know you are real? What if everything you perceive, your memories, your sense of self, even the universe around you, is an illusion, a fleeting fluctuation in the vast emptiness of space? Let's dive into this paradox in extreme detail, exploring its premise, implications, and possible resolutions. The premise: random fluctuations in an infinite universe. The Bootstrap Brain Paradox is rooted in the laws of thermodynamics and statistical mechanics, particularly the concept of entropy. Entropy is a measure of disorder in a system, and the second law of thermodynamics states that entropy always increases over time. However, in an infinite universe, even the most improbable events can occur given enough time. 1. The nature of quantum fluctuations. In a universe governed by quantum mechanics, particles and energy can fluctuate randomly. These fluctuations are normally tiny and short-lived, but in an infinite universe with infinite time, even the most improbable fluctuations can occur. This includes the spontaneous formation of complex structures, such as a fully conscious brain. Boltzmann brains. A Boltzmann brain is a hypothetical self-aware entity that arises from a random fluctuation in the vacuum of space. It would have all the perceptions, memories, and thoughts of a real person, but it would exist only for an instant before dissipating back into chaos. Statistical mechanics. According to statistical mechanics, the probability of a fluctuation decreases exponentially with its complexity. However, in an infinite universe, even events with astronomically low probabilities become inevitable. 2. The infinite universe hypothesis. The paradox assumes that the universe is infinite in both space and time. If this is true, then every possible configuration of matter and energy will occur an infinite number of times. This includes not only Boltzmann brains but also entire planets, civilizations, and even entire universes. Eternal inflation. Some cosmological models suggest that our universe is just one of many in a multiverse, where new universes are constantly being born. In such a scenario, the conditions for Boltzmann brains to arise become even more likely. Heat death of the universe. If the universe eventually reaches a state of maximum entropy, heat death, random fluctuations could still produce Boltzmann brains, even in a seemingly lifeless void. The paradox. Are you more likely to be a Boltzmann brain? The Boltzmann brain paradox arises when we consider the statistical likelihood of a Boltzmann brain compared to a real, biological person. The implications are profound and deeply unsettling. 1. Statistical likelihood. In an infinite universe, the number of Boltzmann brains that could randomly form is vastly greater than the number of real, biological beings. This is because a single brain requires far less energy and complexity than an entire planet or civilization. Numbers game. If Boltzmann brains are trillions of times more common than real people, then the probability that you are a Boltzmann brain is overwhelmingly high. Implications for reality. If you are more likely to be a Boltzmann brain, then your perceptions of reality, your memories, your sense of self, even the universe you observe, are likely illusions. 2. The problem of memory and perception. A Boltzmann brain would have no connection to the external world. Its memories and perceptions would be entirely fabricated, created by the random arrangement of particles during its brief existence. Unreliable reality. If you are a Boltzmann brain, everything you think you know about the world, your past, your identity, the laws of physics, could be completely false. The illusion of time. A Boltzmann brain might perceive time as passing, but in reality, it would exist only for an instant. This raises questions about the nature of time and consciousness. 3. The paradox of existence. The Boltzmann brain paradox forces us to confront the possibility that our existence might be a statistical fluke. If the universe is infinite and eternal, then the most likely explanation for our consciousness is that we are random fluctuations, not real beings in a real universe. Possible resolutions to the paradox. The Boltzmann brain paradox is deeply troubling, but scientists and philosophers have proposed several ways to resolve or mitigate it. Let's explore these in detail. 1. Finite universe. One way to avoid the paradox is to assume that the universe is not infinite. If the universe has a finite size and lifespan, then the probability of Boltzmann brains forming becomes negligible. Cosmological evidence. Observations of the cosmic microwave background suggest that the universe is flat and infinite, but this is not certain. If the universe is finite, the paradox might be resolved. Heat death constraints. Even in a finite universe, the heat death scenario could still allow for Boltzmann brains, but their likelihood would be much lower. 2. The anthropic principle. The anthropic principle states that we observe the universe the way it is because it allows for our existence. In the context of the Boltzmann brain paradox, this means that we are more likely to be real, biological beings in a structured universe than random fluctuations. Structured reality. The anthropic principle suggests that the universe must have certain properties, for example, low entropy, to allow for the existence of observers like us. This makes Boltzmann brains less likely. Self-selection. If Boltzmann brains are vastly more common, why do we perceive ourselves as real beings in a real universe? The anthropic principle argues that we are biased toward observing a universe that supports our existence. 3. Cognitive bias and the nature of consciousness. The Boltzmann-Brain paradox assumes that self-awareness is as easy to generate randomly as it is to evolve through natural processes. However, consciousness might be far more complex than the paradox suggests. Complexity of consciousness. The human brain is an incredibly complex organ, shaped by billions of years of evolution. It is unlikely that a random fluctuation could replicate this complexity. Emergent properties. Consciousness might be an emergent property of complex systems, not something that can arise from a simple arrangement of particles. 4. New physics. The paradox relies on our current understanding of physics, which might be incomplete. New discoveries in quantum mechanics, cosmology, or consciousness studies could provide a way out. Quantum gravity. A theory of quantum gravity might reveal that Boltzmann brains are impossible, or that the universe has properties that prevent them from forming. Consciousness as fundamental. Some theories suggest that consciousness is a fundamental aspect of the universe, not something that can arise randomly. Are you real? Or are you a fleeting illusion? The Boltzmann-Brain paradox forces us to confront the fragility of our existence and the limits of our understanding. If the universe is infinite and governed by the laws of statistical mechanics, then the most likely explanation for our consciousness is that we are random fluctuations. But if the universe is finite, or if consciousness is more complex than we realize, then we might be real beings in a real universe. Ultimately, the paradox is a reminder of how little we know about the nature of reality. It challenges us to question our assumptions and to seek deeper answers about the universe and our place within it. Whether we are Boltzmann brains or real beings, the search for truth is what makes us human. The black hole information paradox. Does information ever truly die? The black hole information paradox is one of the most profound and unresolved problems in modern theoretical physics. It sits at the intersection of quantum mechanics and general relativity, two of the most successful yet seemingly incompatible frameworks for understanding the universe. At its core, the paradox asks, what happens to information that falls into a black hole? Is it destroyed, or is it preserved in some form? Let's explore this paradox in extreme detail, examining its origins, implications, and the leading theories that attempt to resolve it. The contradiction, quantum mechanics versus general relativity. The black hole information paradox arises from a fundamental conflict between two pillars of modern physics, quantum mechanics and general relativity. To understand the paradox, we need to examine the principles of each theory and how they clash in the context of black holes. 1. Quantum mechanics. Information is eternal. Quantum mechanics is the framework that governs the behavior of particles at the smallest scales. One of its core principles is the conservation of information. This means that information about the state of a system can never be lost, it can only be transformed or redistributed. Unitarity. In quantum mechanics, the evolution of a system is described by a unitary operator, which ensures that information is preserved over time. If you know the state of a system at one time, you can, in principle, reconstruct its state at any other time. No hiding. Information cannot simply disappear. Even in chaotic or complex systems, the information is still there, just scrambled or encoded in a different form. 2. General relativity. The singularity. General relativity, Einstein's theory of gravity, describes black holes as regions of spacetime where gravity is so intense that nothing, not even light, can escape. At the center of a black hole lies the singularity, a point where density becomes infinite and the laws of physics as we know them break down. Event horizon, the boundary of a black hole, called the event horizon, is the point of no return. Once something crosses the event horizon, it is inexorably pulled toward the singularity. Information destruction. According to classical general relativity, anything that falls into a black hole is crushed into oblivion at the singularity. This includes all information about the object's properties, such as its mass, charge, and quantum state. 3. The paradox. The contradiction arises when we combine these two principles. Quantum mechanics says information cannot be lost. General relativity says black holes destroy information at the singularity. If both theories are correct, then black holes must somehow preserve information while also destroying it, a logical impossibility. This is the essence of the black hole information paradox. The origins of the paradox. Hawking radiation. The paradox was brought into sharp focus by Stephen Hawking's groundbreaking work in the 1970s. Hawking discovered that black holes are not completely black, they emit radiation due to quantum effects near the event horizon. This phenomenon, known as Hawking radiation, has profound implications for the fate of information in black holes. 1. How Hawking radiation works. Quantum fluctuations. Near the event horizon, pairs of particles and antiparticles constantly pop in and out of existence due to quantum fluctuations. Normally, these pairs annihilate each other almost instantly. Particle escape. Occasionally, one particle falls into the black hole while the other escapes into space. The escaping particle carries away energy, causing the black hole to lose mass over time. Black hole evaporation. As Hawking radiation continues, the black hole slowly shrinks and eventually evaporates completely. 2. The problem with Hawking radiation. Hawking initially argued that the radiation emitted by a black hole is entirely random and contains no information about the matter that fell into the black hole. This would mean that when the black hole evaporates, all the information about the infalling matter is lost forever, violating the principle of information conservation in quantum mechanics. Possible resolutions to the paradox. The black hole information paradox has sparked decades of debate and inspired numerous theories. While no resolution is universally accepted, several leading ideas have emerged. Let's explore these in detail. 1. Hawking radiation and information recovery. Stephen Hawking later revised his view, suggesting that information might not be lost after all. Instead, it could be encoded in the Hawking radiation in some subtle way. Information encoding. The radiation emitted by a black hole might carry information about the infalling matter, but in a highly scrambled form. Decoding this information would require an unimaginably complex calculation. Soft hair. In 2016, Hawking and colleagues proposed that black holes might have soft hair low-energy quantum fields on the event horizon that could store information about infalling matter. 2. The holographic principle. The holographic principle is a radical idea that suggests all the information contained within a volume of space can be represented as a hologram on the boundary of that space. In the context of black holes, this means that information might be encoded on the event horizon. Add/CFT correspondence. This is a specific realization of the holographic principle, which posits a duality between a gravitational theory in a higher dimensional space, like a black hole, and a quantum field theory on its boundary. In this framework, information about the black hole's interior is stored on its surface. Cosmic hard drive. The event horizon could act like a cosmic hard drive, storing information in a two-dimensional form that can be retrieved when the black hole evaporates. 3. Information leakage. Some theories suggest that black holes might subtly leak information through mechanisms we don't yet understand. Firewalls. The firewall hypothesis proposes that the event horizon is not a smooth boundary but a fiery wall of high-energy particles. This firewall could destroy infalling matter but also release information back into the universe. Quantum tunneling. Information might escape from a black hole through quantum tunneling, a process where particles spontaneously jump across barriers that would normally be impassable. 4. New physics. The paradox might be resolved by new physics that goes beyond our current understanding of quantum mechanics and general relativity. Quantum gravity. A theory of quantum gravity, which unites quantum mechanics and general relativity, might provide a framework for understanding how information is preserved in black holes. String theory. String theory, which posits that particles are tiny vibrating strings, offers potential mechanisms for information conservation, such as brains in extra dimensions. Implications of the paradox. The black hole information paradox is not just an abstract theoretical problem, it has profound implications for our understanding of reality. 1. The nature of information. If information is truly conserved, then everything that has ever fallen into a black hole, every star, planet, and even conscious mind, still exists in some form. This suggests that reality is fundamentally indestructible. 2. The fate of the universe. The paradox raises questions about the ultimate fate of the universe. If black holes can destroy information, does that mean the universe is slowly losing its structure and coherence? Or is information preserved in some hidden form, ensuring the continuity of reality? 3. The limits of human knowledge. The paradox reminds us that there are still deep mysteries in the universe that defy our current understanding. It challenges us to push the boundaries of science and explore new ideas, even if they seem strange or counterintuitive. Final thought, does information ever truly die? The black hole information paradox forces us to confront the deepest questions about the nature of reality. Is information truly eternal, or can it be erased? If information is preserved, where and how is it stored? These questions are not just academic, they touch on the very fabric of existence. As we continue to explore the mysteries of black holes, we may uncover answers that reshape our understanding of the universe. Until then, the paradox remains a tantalizing reminder of how much we have yet to learn. Whether information is lost or preserved, the journey to find out is what makes science so profoundly exciting. The heat-death paradox, the end of everything. The heat-death paradox is a profound and unsettling contemplation of the ultimate fate of the universe. It is rooted in the second law of thermodynamics, which governs the behavior of energy and entropy, and it paints a picture of a distant future where the universe becomes a cold, dark, and lifeless void. Yet, this scenario raises deep questions about the nature of time, existence, and the possibility of renewal. Let's explore this paradox in extreme detail, examining its scientific foundations, implications, and the theories that attempt to resolve or transcend it. The contradiction, entropy and the end of time. The heat-death paradox arises from the interplay between thermodynamics, cosmology, and the nature of time itself. At its core, it is a contradiction between the inevitability of entropy and the concept of time as we understand it. 1. The second law of thermodynamics. The second law of thermodynamics states that entropy, a measure of disorder or randomness in a system, always increases over time. This law is one of the most fundamental principles in physics and has profound implications for the universe. Energy dispersal. As entropy increases, energy becomes more evenly distributed. Useful energy, energy that can do work, is converted into useless heat, which cannot be harnessed. Arrow of time. The increase of entropy is often associated with the arrow of time, the one-way direction in which time flows from past to future. Number 2. The heat-death scenario. In the far future, the universe is expected to reach a state of maximum entropy, often referred to as the heat death. In this state, stars burn out. All stars will eventually exhaust their nuclear fuel and cease to shine. The universe will become dark. Galaxies drift apart. The expansion of the universe will cause galaxies to move farther apart, leaving vast, empty voids. No work can be done. With energy evenly distributed, no gradients, differences in energy, will exist to drive processes like star formation, chemical reactions, or life. Number 3. The paradox of time. If the universe reaches a state of maximum entropy, where nothing changes, what happens to time? Time is often defined by change, the progression from one state to another. But in a heat-dead universe, no change, no time. If nothing changes, does time itself cease to have meaning? Is the universe frozen in an eternal, static state? The end of existence. If time stops, does existence itself come to an end? Or does it simply enter a new, incomprehensible phase? Possible resolutions to the paradox. The heat-death paradox is deeply troubling, but scientists and philosophers have proposed several ways to resolve or transcend it. Let's explore these in detail. Number 1. Quantum fluctuations in cyclic universes. Even in a heat-dead universe, quantum mechanics suggests that random fluctuations can occur. These fluctuations might provide a way for the universe to reset itself. Quantum tunneling. In a universe at maximum entropy, a quantum fluctuation could theoretically create a new region of low entropy, sparking a new Big Bang. This would lead to an infinite cycle of universes being born, dying, and being reborn. Eternal inflation. Some cosmological models suggest that our universe is just one of many in a multiverse, where new universes are constantly being born from quantum fluctuations in a larger meta-universe. Number 2. The multiverse hypothesis. The multiverse hypothesis posits that our universe is just one of many, each with its own physical laws and constants. While our universe might be heading toward heat death, others could be vibrant and full of energy. Parallel universes. In a multiverse, the death of one universe does not mean the end of existence. Other universes could continue to thrive, ensuring that life and complexity persist somewhere. Different laws of physics. Some universes might have physical laws that prevent heat death, allowing for eternal complexity and activity. Number 3. New physics and the limits of entropy. Our current understanding of entropy and thermodynamics might be incomplete. New discoveries in physics could reveal that entropy is not an absolute limit. Negative energy and dark energy. Some theories suggest that dark energy, which drives the accelerated expansion of the universe, could have properties that counteract entropy. Emergent structures. In a heat-dead universe, new forms of matter or energy might emerge, creating structures and processes that we cannot yet imagine. Number 4. The nature of time. The heat-death paradox challenges our understanding of time. If time is defined by change, what happens when change ceases? Some theories propose alternative views of time that could resolve the paradox. Timeless universes. In a universe without change, time might become irrelevant. Existence could continue in a timeless, static state that is beyond our current comprehension. Eternalism. Some philosophical theories suggest that past, present, and future all exist simultaneously. In this view, the heat-death of the universe is just one slice of a larger, eternal reality. Implications of the paradox. The heat-death paradox is not just an abstract theoretical problem, it has profound implications for our understanding of existence, time, and the universe. Number 1. The fate of life and intelligence. If heat-death is inevitable, what does that mean for life and intelligence? Will all civilizations eventually face the same fate, or is there a way to transcend the limits of entropy? Cosmic purpose. The paradox raises questions about the purpose and meaning of existence. If the universe is destined to end in a featureless void, does anything we do ultimately matter? Transcendence. Some thinkers speculate that advanced civilizations might find ways to escape heat-death, perhaps by creating new universes or transitioning to a different form of existence. Number 2. The nature of reality. The paradox challenges our understanding of reality itself. If the universe can reach a state where time and change cease to exist, what does that say about the nature of existence? Illusion of permanence. The paradox suggests that permanence might be an illusion. Everything we know, stars, planets, life, is temporary, destined to fade into the void. Infinite possibilities. On the other hand, the paradox opens the door to infinite possibilities. If the universe can reset itself or if new universes can emerge, then existence might be eternal in some form. Number 3. The limits of human knowledge. The heat-death paradox reminds us that there are still deep mysteries in the universe that defy our current understanding. It challenges us to push the boundaries of science and explore new ideas, even if they seem strange or counterintuitive. Final thought. What comes after the end? The heat-death paradox forces us to confront the deepest questions about the nature of reality. Is the universe destined to end in a cold, dark void, or is there a way for existence to continue, even in a form we cannot yet imagine? If heat-death is inevitable, what comes after the end? Does existence fade into eternal stillness, or does something even stranger emerge? As we continue to explore the mysteries of the universe, we may uncover answers that reshape our understanding of time, entropy, and existence. Until then, the paradox remains a tantalizing reminder of how much we have yet to learn. Whether the universe ends in heat-death or transcends it, the journey to find out is what makes science so profoundly exciting. The cosmos refuses to be simple, and as long as we keep asking questions, we remain part of its infinite mystery.